Hello, everybody. Welcome to a section of calculus. And today we will be talking about the Rolle's theorem and also the mean value theorem. So this is the chapter 4 portion of it, which means now we're going to start looking at some of the applications of derivative, like what can you possibly do with it besides solving for a tangent point, as we said last time. So here, let me go ahead and introduce first the Rolle's theorem, and then afterwards the mean value theorem, and see how they can actually work out for you. So here in the Rolle's theorem, here's what it says then. If you have f as a function and it's differentiable within an interval of a to b for x, and also f is continuous on the interval, closed interval of a to b, and finally, if f of a is equal to f of b, then the following statement is going to be true. There exists a value c in the open interval of a to b such that f prime is equal to 0. So first of all, let's go ahead and draw a picture so you can understand what it means to what this Rolle theorem actually means. So we're going to kind of work backward here. I'm going to go ahead and start with the following. I'm going to go ahead and start with the fact that we have A, we have B for x, so that's going to be our interval. And the condition over here is that it is continuous, and also f of a is equal to f of b. So that means that they share the same y value. So that means that it ends vertically at the same value. So over here, let's just go ahead and say that then. So this, you can see that f of a is equal to f of b in this case. Now, what's going to happen here is that I can draw any curve so long as it is differentiable and also continuous. So why don't I just go ahead and draw any old curve? So maybe something like the following. The conclusion, according to the Rolle's theorem, is that there exists a value c inside this interval such that f prime of c is equal to 0. And yeah, you can see how that actually works out, because you'll notice that here you can see where the derivative is equal to 0, and over here where the derivative is also equal to 0. So in this case, there are two values of c. What the Rolle theorem's proof is that there will be at least one. So maybe there's 1, maybe there's 2, maybe there's 50. Who knows? Depends on what the graph actually looks like. Can it be another variation? Sure. Let's go ahead and see if we can change the conditions a little bit and see if we can come up with the same conclusion. So long as the endpoints are the same thing vertically, and then we just draw any old graph. Let's say this time, maybe you can just draw a graph that looks something like this. It has to go up and then afterward come back down. And in this case, yeah, the Rolle's theorem is still going to hold true, because you can see that somewhere in there, the graph has a derivative where it's going to be 0. So that's basically going to be the Rolle's theorem then, okay? So let's go ahead and see an example of how the Rolle's theorem actually works. Show that f of x is equal to 2x minus 1 minus sine of x is equal to 0 only has one solution. So this kind of goes back to chapter 1 or chapter 2 when we introduced the intermediate value theorem, right? So here we can prove it that way, but let's go ahead and use the Rolle's theorem just to see if it's any easier or more convenient then. So what we're going to do is I want to prove that there's only going to have one solution. So what we'll do is we're going to prove this by contradiction. So kind of going back to your geometry days, what that means is I am going to assume the negation of what I'm trying to prove. So the statement here says that I want to show that there's only going to have one solution. Let's go ahead and assume that there are more than one solution. Maybe there's 2 solutions or 3 solutions and so forth. Okay, so there it is. Solution is going to be proof by contradiction. Assume that there exist 2 or more solutions. Then, according to mean value theorem, then that means that this has to be true right here. If I call the solution, one of them, let's go ahead and call it A, and then let's go ahead and call the other one B, then according to Rolle's theorem, then that means that there should be a case where f of A is equal to f of B, which is equal to the 0 that you see that we're having set up. Well, that is according to Rolle's theorem so far. So now let's go ahead and solve for the derivative f prime to see exactly what's happening, because I need to figure out what is that c value such that f prime of c is equal to 0. Well, here's where the contradiction comes in, because if you notice, I did solve for the derivative, but the problem is that, actually I erased it, so hopefully it's okay. Fortunately, we didn't really need too much of that part. Here is the derivative. F prime of x is equal to 2 minus cosine of x. And if you look closely to that equation, there's no way for this to be equal to 0 because the domain, the range of this function is somewhere between 1 and 3 because of the cosine graph. So because your graph of f of x, so because your f prime is always going to be greater than 0, then that means it's not going to satisfy the Rolle theorem. And as a result, it's going to be a contradiction then. Okay, so that's going to be one use of the Rolle's theorem. Now, what I want to do is I want to take Rolle's theorem and apply it to like a better scenario, something that's a little bit less restricted. And this right here is probably going to be used a lot more often than the Rolle's theorem. This is what is known as the mean value theorem. So you'll notice that the setup for the mean value theorem is exactly the same thing as the Rolle's theorem. The if statement is that if f is differentiable on a to b, and if f is continuous on the closed interval of a to b. Now, the restriction that we don't have in this case is f of a is equal to f of b. So what that means is I can actually have it so that the y values are not equal to each other. Then the conclusion to the mean value theorem is that there exists a value c within the interval of a to b, same as before, such that now this time we have a different equation. F prime of c is equal to f of b minus f of a, all divided by b minus a. So let's go ahead and translate that and draw it out so you can see what that's actually saying. So first of all, again, we're going to have a graph. We're going to have an interval from a to b, right? And let's just go ahead and draw some arbitrary y value, which is going to be f of a. So that's going to be somewhere over here. Then we're going to go ahead and draw some arbitrary value, which is going to be called f of b. Now, it could be the case where f of a is greater than f of b, but we're just going to draw something just to work with it, okay? So what we can do is now we can sketch out a graph of f of x, and this is just going to be any old sketch so long as, again, it is differentiable and also continuous. So that means we just have to draw a smooth curve connecting from one point to the other. So just like before, what we'll do is we're going to go ahead and maybe draw some curve. Okay, it's just something really weird looking or whatever, doesn't matter. So there it is. That's definitely differentiable everywhere and continuous everywhere. So now let's go ahead and decipher the second part of the mean value theorem. Here, you'll notice that on the right-hand side, we have f of b minus f of a all divided by b minus a. That right there is the average rate of change within that interval, right? It's the average rate of change in the interval. So that means it's going to be this guy right here, okay? And so now if I'm looking for f prime of c such that it's equal to the average rate of change, then that means that here for my graph, no matter how I sketch it out, so long as it is differentiable and continuous, they're basically saying that somewhere within the interval of a to b, that there is an instantaneous tangent, which we're going to go ahead and call f prime of c, that is going to be equal to the average rate of change. So repeat it one more time. There is going to be at least one tangent that is going to be equal to the average instantaneous rate of change. And here in my picture, you can see that, yeah, there are definitely a few of them. One is going to be over here. Another one is going to be over here. And then another one is probably going to be somewhere over here. Okay, so there it is. That's going to be mean value theorem. So in relation to the two, the mean value theorem doesn't have the restriction that the endpoints have to have the same values of y. Rolle's theorem is very restricting in the sense that the y values have to be the same, so that's why mean value theorem is actually used more often than Rolle's theorem. And in fact, some people might say that the Rolle's theorem is basically kind of like a subset or like a sub-scenario of the mean value theorem then. All right, so now let's go ahead and apply this to some problems just to see how this actually works out. Here's an example. Find the value or values of c that satisfy the mean value theorem for f of x is equal to x divided by x plus 2 on the interval of 0 to 4. Now, you'll notice that on the right-hand side, I basically kind of set up the procedure that we're supposed to do this problem with. First, I'm going to find the average rate of change from 1 to 4 because that's going to be my interval. Next, I'm going to go ahead and solve for the derivative of f prime of x in order to set up the tangent. And then I'm going to go ahead and set the average rate of change equal to the tangent, so then that way we can find those values of c. So let's go ahead and see if we can do that then. first, let's go ahead and solve for that average rate of change. So the average rate of change within the interval from 1 to 4, that is going to be equal to f of 4 minus f of 1, all divided by 4 minus 1. So numerically, that looks like it's going to be 4 over 6 minus 1 over 3, and all divided by 3 in this case. To make my life a little bit easier, I think I'm going to go ahead and multiply everything by 6 to both top and bottom to clean up the math. I'm going to get 4 for the first part, minus 1/3 of 6, that's going to be equal to 2, and then all divided by 18. So the average rate of change, or the average slope in this case, is going to be 1/9 then, because it's going to be 2 out of 18. Now what we're going to do is we're going to go ahead and solve for the derivative of f prime of x. So that way we can figure out where what the tangent is going to be like. So the tangent, the derivative in this case, we're going to have to use the quotient rule. So it's going to be the bottom equation multiplied by the derivative of the top minus the top multiplied by the derivative of the bottom. Oops, messed up on the derivative of the bottom. Let me go ahead and change that. It's supposed to be 1. And then all that is divided by the bottom squared. So x plus 2 quantity squared. Let me do a little bit of cleanup here. And then we're going to go ahead and set the equations equal to each other. By the way, right now, we're over here in the second step. So the top part, we have x plus 2 minus x. So that gives us plain old 2, because the x over here and the x over here cancels out. All divided by x plus 2 quantity squared. And if you remember, we're going to take that and set it equal to our 1/9, which is supposed to be equal to our average rate of change within that interval of 1 to 4. So now we're going to go ahead and solve for the value of x or c, doesn't matter which one it is. So then that way we can figure out where's that point then. So we'll go ahead and cross multiply. So if we cross multiply here to here, we are going to get 18 is equal to x plus 2 quantity squared. Take the square root of both sides. So we have now the square root of 18 is equal to x plus 2. And that square root of 18 should technically be a plus or minus, because there should be 2 solutions. Clean that up a little bit. Maybe I'll go ahead and say that this guy right here, the square root of 18, that's the same thing as plus or minus 3 root 2. And finally, x is going to be isolated by putting the 2 onto the other side. So negative 2 plus or minus 3 root 2 would then be our solution. Now be very careful. Yes, there are 2 solutions that we solve for, but I think only one of them actually works, because if you recognize, according to our interval, we need the solution to be between 1 to 4. So to find out which one that is, I think I'm probably going to take the positive one, because you start off with negative 2. So my final solution is going to be negative 2 and then plus 3 root 2 then. So that's going to be my value of c, where the derivative is going to be equal to the tangent. All right. All right, so now let's go ahead and take a look at this last example over here then. Let f be continuous and differentiable. That is basically key right there for my mean value theorem. And in fact, it's probably key for most of the stuff that we're going to be doing in calculus first semester. And f prime is somewhere between 3 and 5 inclusively. Show that 18 is less than or equal to f of 8 minus f of 2, which is going to be less than or equal to 30. The solution here is, well, I just basically need to show that this bottom equation is going to be true. So let me go ahead and kind of highlight this for right now, and let's go ahead and see what we can get out of it. First of all, I noticed that we have f of 8 minus f of 2, which is what I noted over here. So that tells me that they probably want us to use some sort of mean value theorem where the interval is supposed to be somewhere between 2 and 8. So let's go ahead and set up the mean value theorem then. We know we can do that because, first of all, f is continuous and differentiable. So by the mean value theorem, we can say that there exists a value c such that f prime is going to, f prime of c is equal to f of 8 minus f of 2, all divided by 8 minus 2. So by setting up this mean value theorem, we're basically setting up the part of the equation that we want, which is over here. Now, let's go ahead and go a little bit further. We're told that f prime is always between 3 and 5 inclusive. So what that means is, if I were to take this guy right here and this guy right here, I can go ahead and say the following. F prime of c is equal to f of 8 minus f of 2 all over 8 minus 2 because the mean value theorem. And that is going to be in between 3 and 5 because, well, f prime of c, that's basically this part over here. X basically the same thing as c, whatever you want to call it, dummy variable. Hey, look at what we have and look at what we want. I think we're pretty close. We have our f of 8 minus f of 2. And the bottom part is equal to 6 because f 8 minus 2. And if I multiply both sides by 6, I think we now have our solution then. So f of 8 minus f of 2 is bounded in between 3 times 6, which is 18, and 5 times 6, which is equal to 30. So there is your proof then. All right, I think that'll do it then. Thank you so much for watching.